In the last lecture, we followed the trajectory of the long amplifier chain, the trajectory of this chain over the years, what happened to it over the years. So, there was the free running laser, then the Q switched laser, then the mode locked laser, and all emphasizing on how to using all these types of laser to extract more and more power from the amplifier chain. So, finally, there was a bottleneck for over 20 years when the peak power was not increasing, and then a very new technique called the chirp pulse amplification was discovered by Morrow and Strickland, and for that they were also given the Nobel Prize in 2018. So, with this bottleneck gone, there is no stopping the kind of powers, peak powers that were achievable. So, petawatt has become now almost like everyday affair. It is easy to get a petawatt level output from a laser chain. Okay. So, let us go on beyond that. So, I think I should describe what is a chirped pulse amplification, okay, and what is the word chirp in chirp CPA for short, refers to, and the process is where the frequency of a pulse of light changes progressively over time. Okay, that is chirp pulse. And why should it have this word chirp? You know, it has this word chirp because that's referring to, I think, referring to the bird calls, which also follow this similar kind of principle in the sound that they make. You know, they start off with the one frequency sound and they go on to some higher or lower frequencies. There is a graded increase or decrease in frequency, which we call chirp. So, I think that is what it refers to, or that is the analogy put here, and so this word chirp pulse has become usual for a laser amplification process. Okay. So, let me describe this chirp pulse through these graphs here. So, this is a laser pulse in time, and this is the amplitude of the pulse. Okay, I have given a normalized amplitude, so 1, and this is the time, a square pulse, just to be simplistic in my explanation. Now, this is in time, but I have again this pulse in time, but then the y axis is not the amplitude, but the frequencies. There is a central frequency which is f0. f0 is the central frequency here, and there are frequencies above f0 and below f0. Okay. And along the time of this pulse, these frequency increase gradually. This is called the chirp. That means you started off with a low frequency, and slowly over this time of the square pulse you have increased the frequency. Okay. Another way of putting it is like this in case of the signal amplitude or the electric field associated with that light pulse. So, here if you see this oscillation, this definitely has a longer wavelength or a shorter frequency, a larger short frequency. Here as you go through, the wavelength becomes shorter and shorter, and the frequency becomes larger and larger. So, over this length of time you have changed from a short frequency to a high frequency, or a long wavelength to a short wavelength. Okay. And it has happened linearly over time. So, it is called a linear chirp. Not that all systems can give you a linear chirp, but we strive to use those systems where the chirp is linear, so that you are able to handle the pulse much more easily. Okay. So, in case of the light, now you have understood what chirp means. Now, how is this chirp used in my laser system? In chirp pulse amplification, or how is the chirp used in the amplification process? Okay. In a CPA system, a short laser pulse is first stretched in time by introducing a chirp. Stretching ensures energy distribution over a longer pulse. Then amplification without damage to the medium. Then the pulse is compressed back to its original duration. All right. So, this is what I show pictorially. You start off with an ultra short pulse. This is here. I will talk in terms of ultra short because we are talking in terms of femtosecond pulses. So, I have this ultra short pulse and then I stretch it in time. Okay, this is the time axis, the bottom dark black line is the time axis. So, my initial seed pulse is an ultra short pulse, and this is what happens to the pulse. And when I show this colored, like the spectrum out of a prism or breakup of all the colors, that is because all these colors have separated out over this time duration. So, this is just one way of showing that. Okay. I have increased the length of the pulse, as you can see in the picture. This is a short pulse and this has become a long pulse. Now, this long pulse goes through an amplification process and it gets amplified. It still remains a long pulse. The pulse is long, but it has been amplified, okay, keeping that whole spectrum intact. Whatever was the spectrum here of the ultra short pulse, the same remains here after stretching, the same remains here after amplification. Okay. Only the time has changed. And then at the end of the amplification, when you have amplified to your desired value, amplified to an energy of your desire, then you compress the pulse. So, when you compress the pulse, you bring it back to its original pulse length, but of course, the amplification is more. So, that is why I show a height here, while this height is small, height of the pulse is small. Here it is more because it is amplified, but the width of the pulse, temporal width, is the same as the temporal width here. Okay. Now, there are some things where people do get confused. When I talk about a short pulse, I assume that the bandwidth is very large. Not assume, you have to have a large bandwidth, because if you remember the time bandwidth product, delta tau delta nu is almost equal to 1. Okay. So, if your delta nu is large, okay, then your delta t is small. Okay, these are inversely proportional to each other. Okay, the bandwidth is large, your time becomes short. Okay. So, but in this case, I have kept all the frequency within this pulse here. I have not changed the bandwidth. The bandwidth is in the realm of the spectrum, and what I am showing here is in the realm of time. Okay. So, I have stretched it in time, not stretched it in spectrum. The spectrum remains the same as the seed pulse. Okay. So, what this time bandwidth product actually shows is that if you have a certain amount of spectrum, then you can reduce the pulse to delta t. Need not be that the pulse is delta t, it need not be possible in practical sense. But you cannot have a short pulse if you do not have that particular delta nu. That is what you need. So, here what I want to say is that I have increased the pulse length, but I have not touched upon delta nu at all. I have not tried to destroy delta nu in in going through this process. And here I show it as white because all the frequencies that are present in this ultra short pulse cannot be distinguished over time. All those frequencies exist at this point, at this point, at this point, at this point, at all the points of the pulse. It's evenly done. While when I have stretched it, I have put the longer frequencies here, the longer wavelengths here and the shorter wavelengths here, or it could be even the other way around. So, that is what I have done. In the original seed pulse, they all exist, all these frequencies exist at every instant of time in that short pulse. But in a stretched pulse, it has been chirped. Because it has been chirped, as you can see here, the different wavelengths are spanned over that complete time, which is shown here also. The different wavelengths are spanned over this whole pulse length, and as a result that pulse length has increased. Okay. So, this is the technique of chirped pulse amplification. So, I amplify it only after I have chirped the pulse, or I amplify it only after the pulse length has increased. Okay. If the pulse length increases, that means the energy that I am able to extract is much more from the amplifiers, and at the same time I have the peak powers are much lesser, the intensities automatically become much lesser while this pulse is passing through the amplifiers, and I do not destroy the amplifiers. Not only destroy, I do not bring any nonlinear effects which can mar the whole amplification process. So, the whole idea is to prevent the amplifiers from the destruction, whether physical or because of the nonlinear effects that is brought in. You have got a hint of some of the nonlinear effects that happen even in the long pulse laser chain, where I talked about birefringence, self-focusing, streaking, such things, gain narrowing. The same things apply here. Okay. So, I want a large energy output, I want a large peak power output, but at the same time I do not want to destroy the amplifiers. The destruction of the amplifiers was the bottleneck, and with this invention of chirped pulse amplification, that has gone. So, in the final pulse that I get here, it has saved the amplifiers, at the same time I have been able to extract a large energy and therefore a large peak power. Okay. This is the whole idea of the chirped pulse amplification. But it is not devoid of problems, it has a lot of problems which have to be solved, of course. Okay. So, before I go into the solution of all those problems, I think you must understand what is group velocity dispersion. Group velocity dispersion, or GVD for short. See, such a phenomenon of group velocity dispersion would not have come into the picture if you are talking of long pulse length, or in a long pulse length of microsecond pulse, or even a nanosecond pulse. You know, it will not come into the picture. But it does come into the picture because it is a very ultra short pulse length that we are talking about, and we are talking about very large bandwidths, lots of frequencies within that same pulse which exist. So, what are the distortions that group velocity dispersion brings about to a temporal pulse, okay, a pulse in the time domain? That is what I want to describe here. Okay, so, I have written that here in short. Since ultra short pulses have a very large bandwidth, GVD becomes a very big issue, and velocity of the light in a dispersive medium is dependent on its wavelength, that you already know. resulting in distortion of a femtosecond pulse. So, in a dispersive medium, what happens? Vg stands for the velocity, group velocity. I will just tell you what I mean by group velocity. So, the velocity of the blue light is less than the velocity of the red light, or the refractive index of the blue light is more than the refractive index of the red light. Okay. So, you can get a glimpse of this, say even in the kind of prism experiments that we used to do, and the light breaks up into all its colors. Okay. That is because to the light, the medium of the prism is presenting in such a way that different wavelength sees a different refractive index. So, N blue, the blue light, refractive index for the N blue is larger. It presents a larger refractive index to the blue light and presents a smaller refractive index for the red light. Okay. So, obviously, if the refractive index changes, the velocity of that light also changes. So, these are sort of complementary to each other. If the velocity is increasing, then the refractive index is less, or the other way around. Okay. So, this is the basis of your group velocity dispersion. So, all these wavelengths are dispersing away in space, or in the medium, in a medium through which this light is passing. Okay. Suppose I consider this as a pulse here. The green light gives you that electric field. So, the electric field is just this, and the green line is giving you the envelope. Okay. The electric field is in arbitrary units, and this is a wave packet. Try to recall what the lecture on mode locking, where two waves or more than two waves, when they superimposed with each other, resulted in beat waves or wave packets. Okay. Recollect that. That means all these frequencies are packed into this one pulse. All the frequencies or all those modes are equivalent to frequency. So, you have this number of frequencies all packed into this pulse. So, it is called a wave packet. Okay. So, now in this wave packet, what happens is you have something called the velocity of the group. This total thing forms a group. This whole wave packet forms a group. So, the velocity at which this is traveling in your medium, that is one. And there is something called the phase velocity also, I will come later, where these individual frequencies are moving. So, the individual frequencies are also moving, and at the same time this whole packet of light is also moving through. Okay. The red line here just gives you the intensity. Intensity is electric field mod square, as you can see here. So, it shows as a pulse like this. So, this is actually the actual pulse in time. Here I have given the time axis here. So, this is the time, and of course, the wave packet in this time. So, the intensity gives you the actual pulse. So, the actual pulse is this short, and it is packed with all these frequencies sitting inside, and each of those frequencies have a certain velocity of movement, and and the group as a whole is moving together. Okay. Yeah, you can visualize it a bit in this graph. Okay, if you see this dotted portion, that is one wave packet. It is just gone behind a bit. This is my initial start of the wave packet. And then as this wave packet has traveled inside a medium, see it slowly elongates into a longer pulse. This is all in femtoseconds time scale. Just see the femtoseconds time scale. So, it has elongated into a long pulse. Okay. As it is just traveling through, the chirp is brought about, a linear chirp, or because of that chirp, that whole thing, it goes this way. So you can see that gradual increase in the length of that pulse from the original one. Okay. And the intensity also has gone down a little bit. Here, if you can see, the intensity here, the amplitude is higher. Here, the amplitude is a bit lower, and obviously, then the intensity also will become a bit lesser as compared to this. So here is this pulse, and then I show it in the femtosecond time scale is because it has happened in the femtosecond time scale realm. If it were a much longer pulse, there was no need to worry about it. It happens in this femtosecond, say, time scale. So in a nanosecond, it will hardly make any difference. But once your pulse is in the femtosecond time scale, your pulse length has changed from this original one to this long one. Okay. And the moment the time becomes longer, your peak powers itself go down. So you really have to bother about the changes brought about by this group velocity dispersion. Now, mathematically putting it, just defining it in a more precise way. Here I have just given you an understanding of what group velocity dispersion is. But if you put it precisely, then group velocity dispersion is given as d by d omega 1 upon Vg is equal to the derivative of dk by d omega, where k is the wave number or wave vector which you have come across before, and wave vector is omega by c. Here I have put in the refractive index because it is passing through a medium with a certain refractive index, and the refractive index is different for different wavelengths. So definitely the refractive index comes into play and it affects your k vector. So dk by d omega, omega are the different frequencies. So the derivative of this gives you the group velocity dispersion. So the group velocity dispersion is defined as d square k by d omega square. Okay. Intuitively you can understand this because k is dependent on the frequency because of the refractive index. So obviously it gives a kind of dispersion which is given by d square k by d omega square. Okay. N omega here I have written as the refractive index. Okay. So this is group velocity dispersion. See, in this slide I will just talk of the dispersion of light basically. They are all related, group velocity dispersion or dispersion of light. It is all the dispersion of the different wavelengths itself. Okay. And the best you can see is you can get a group velocity, a dispersion. A good example is this prism, as I told you before. All these wavelengths are dispersed of. Okay. See, this has been known years and years before. We have studied it in optics for so many millennium, but then it has been used very cleverly by Gerard Moreau and Donna Strickland, which led to that Nobel Prize winning, and they have used it cleverly for this in case of chirped pulse amplification and to amplify that whole pulse. So here it is. So you can get group velocity dispersion with the use of a prism. You can get chromatic dispersion or group velocity dispersion when you pass a pulse through a fiber. This is a fiber. All these multiple reflections within the fiber. You keep on increasing the length of the fiber depending on how much dispersion you need or how long you want the pulse to grow. So this is a fiber through which it goes to. And another thing that you can do is have a grating. The grating also gives you this angular dispersion. Okay. And each of these wavelengths arrive at a different point at different times, exactly like in the prism. Okay. The red light arrives at a particular time, at a particular space, and the blue light arrives at that same space at a different time. The purple light arrives at a different time. So, you know that delay in time for each of these wavelengths give rise to the total spread of the temporal profile. Okay. You can put it a bit now, to put it exactly or mathematically, let us just go through this. So, most of the mathematical part is shown in green. If I start off with this Vp, no, let me start here. So, any wave, any electromagnetic wave, this is one way of describing GVD. Any electromagnetic wave is quite often represented by e to the power minus I omega t minus kz. Okay, it is proportional to this. So, omega is the frequency and k is the wave number, we have done this before, and z is the distance it has to travel. Let the phase be, you know what is inside this bracket is called the phase. The phase has not changed, remain constant, or you can say it has remained 0. So, the phase is omega t, suppose the phase has not changed, omega t minus kz is equal to 0. Then z by t is equal to omega by k, just from here. And dz by dt becomes d omega by dk. So, z by t is obviously the velocity, distance divided by time is the velocity. So, that is why Vp, the phase velocity is omega by k, and that is for that individual frequency omega, one frequency, and it is an instantaneous speed of that frequency. But dz by dt, if I have just taken a derivative on both sides, dz by dt will become d omega by dk. Okay. So, the moment it is this, I bring in this because there are a group of velocities, it is no longer one single velocity. D omega by dk, there are a group of frequencies and there are a group of k vectors. So, group velocity is defined by d omega by dk, and k, as you know, is n, I have just repeated it here again, k omega is equal to n omega omega by c. Okay. So, you will see the whole idea of doing this is because I will go ahead and show you each of these. The phase and the time delay and the group velocity dispersion, they are all related to each other, and they all point to the same direction of a lengthening of the pulse. Okay. So, in my next lecture I will tell you about how exactly the pulse lengthens.